Hello everyone, this is our second and last lecture on 3D dynamics. So last time we talked about kinematics in 3D, and today we're going to talk about kinetics in 3D. So as you know, a rigid body in 3D has 6 degrees of freedom, 3 translations, 3 rotations. For translations, the equations of motion are just like what we had in the past, sum F equal ma. And you can write this equation along any 3 set of axes that are perpendicular to each other. Even if they are not perpendicular, you still can write it, but they might not necessarily give you 3 independent equations. But this one is quite easy, no difference than 2D. You have an extra axis. Let's say if you had x and y, now you also have z. The important thing and a little bit more difficult thing in 3D is rotation. Because now your angles go from 1 angle to 3 angles, and you have 3 equations for rotation. So what we try to do here is try to use the matrix notation and write the rotation equations into a matrix format to make it more concise and easier to understand. So if you remember, the general equation for rotation that was always valid regardless of 2D or 3D was sum of the moments about origin, or a fixed point on the rigid body, is equal rate of change of angular momentum h calculated about that point, where h was the definition was, if it was a system of particles, it was summation over the particles of the position vector I cross the linear momentum mvi. And if it was a rigid body, then it was basically an infinitely many particles in a system with very, very small masses. Then instead of the summation, you have integrations. And I have showed you that you can write h, if you remember, to be I times omega, correct? So in 2D, if you remember, in 2D, I showed you that this h, which was, let's say, if the motion was on xy plane, this h was about z-axis. This h about o, or any other axis, which was along the z-axis, this one was equal to I about the z-axis times omega, which was also about the z-axis. Right? So this is what we had in 2D. Now in 3D, you can easily show that the same thing applies with a small difference. So here your h has 3 components, x, y, and z, and your omega has 3 components, x, y, and z, and your I is now a matrix. We call him the inertia matrix. And this inertia matrix is Ixx, negative Ixy, negative Ixz, and then negative Iyx, Iyy, negative Iyz, and the same thing. So the diagonal elements, they don't have a negative sign behind them. Any off-diagonal element has a negative sign. And the matrix is, of course, the transpose of the matrix is the same as the matrix, right? So it's symmetric. So in 3D, as I said, the same notation exists, but now here we have vector h is equal to matrix I times vector omega. So this guy is a 3 by 1, omega is a 3 by 1, and this I, as I said, is a 3 by 3 matrix. And as I said, I is a matrix where the diagonal elements do not have a negative sign behind them, and then the off-diagonal elements, they do have a negative sign. Okay? And IZY is the same as YZ, XZ is the same as ZX, and XY is the same as YX. So as I said, this matrix is symmetric. So we can write it this way, and so Now, if we apply that formula that I just showed you, if I plug it back here into this moment equation, then I will get my three equations for what? For rotation, of course, right? Because this moment has three components: moment x, moment y, moment z. And then if you can take derivative of these h components, if you expand this vector matrix notation, this is the expansion version, and you can get your moment equation. And here is what is done in the textbook, and then came down to this big set of equations that you can see here. Now here, I would like to make life a little bit easier for you. So I would write it as in vector notation again, that you can see down below. So the thing is this. So I'm saying that M is about O, let's say, is dH with respect to O over dt, which is d over dt of I omega, correct? So now, how do I calculate this? So here, I times omega is a vector, we call it h. And this h, if you remember, in general, it can be measured by what? It can be written, not measured. You can say measured. It can be written or measured or sensed in a secondary coordinate frame, where that secondary coordinate frame itself is rotating about the primary coordinate with angular velocity cap omega. Remember that? So this is what we had last time when we derived this important equation, alpha equal omega dot plus derivative of omega times omega. So we can directly plug this in, or if you remember, again, we are writing this vector omega, or the product of I matrix with omega, we call it h. We are writing that h with respect to the coordinate system xyz, which itself is rotating with cap omega about the primary system. So we are writing h to be hx times I, where I is this unit vector, hy times j, hz times k. And now when I say dh over dt, those h components, okay, they change because what? Because not only their magnitude can change, because the magnitude of components in omega can change, right? So you have d omega over dt, right? d omega x over dt, d omega y or d omega z over dt. Also, they can change because these vectors I, j, and k are rotating with this angular velocity omega, right? So if I go back and show you here, look at this. So this is HOX, correct? HOX. And as I said, H is HOXI plus HOYJ plus HOZK. So now when I take derivative of HOXI, the first component, is going to be the derivative of this whole thing times I. Well, what's the derivative of this with respect to time? These components, ixx, ioxy, and ixz, are constant numbers, so they're not going to change over time. So the change in that is because omega x, omega y, or omega z, they have time derivatives. But also, as I said, it's HOX times I. So maybe none of these is changing, but the vector I, which is attached to the frame rotating by angular velocity cap omega, it's changing because of that. And the change in that vector I, if you remember, was cap omega times I, correct? So if we calculate this, this is going to be this is going to be basically I, right? Correct? Because again, this is the vector that I am taking derivative. So you have the omega dot terms plus what? The change in I omega term because of rotation of the unit vectors. So this is that term because of rotation of the unit vectors, and this is the term because of the omega dot term. So it is going to be I omega dot plus omega cross I omega. Okay, and this is equal to the vector m. If this is with respect to O, then this whole thing is with respect to O, and this whole thing is with respect to O. Okay, so this is going to be the equations for rotation, and the total of the three equations you get from here and the three equations you get from sum f equal ma, we call all these equations of motion of object in 3D, we call them Euler equations. And if you expand that, if you expand the rotation equations, your equations are not going to be super simple looking. Okay, so for example, the x equation is going to have 9 components. Ixx omega x dot minus Ixy omega y dot minus Ixz omega z dot plus cap omega z times this component here, which is hy, plus cap omega y times this component, which is hz. Okay, and the same for moy and moz. So each equation on the right hand side will have 9 terms. Now, you might say, well, what happened in 2D that these equations were so simple? The only equation I had from these 3 giant equations was the equation sum mz was Iz omega z, correct? That's the only thing I had in 2D. Nothing else. What happened? Can you show me that you can go from these big equations back to that simple equation that I have here for 2D cases? And the answer is yes. Let me show you why. So if you want, we can go one by one, and I'll show you why in 2D life is so simple. And then we go back and look at other things in 3D before we use it for a problem. So this is the x equation, moment x. And what do you have? When the problem is in 2D, so in 2D, their only rotation is omega z. There is no omega x, there is no omega y. Both of these guys are 0 as well as their derivatives. So basically it means this term is 0, this term is 0, this one, this one, this one, this one. They're all 0. Correct? Good. Now, what about the rest of it? Since the problem is 2D, there is no moment about x or y. So mox is also 0. So this one is 0. And omega z does exist. What about Ixz and Iyz? So in that problem, whatever shape that you have, if you remember, and this is x-axis and this is y-axis, the I components that you had non-zero were Ixx, it could be non-zero in general, and then what? Iyy and Ixy. These guys could be non-zero because the problem was 2D. And when it's 2D, it's like literally you're not considering the thickness of the object. So Ixz and Iyz were also 0. Izz was not equal to 0 because it was rotation about this z-axis, and it was basically it could be shown if it's thin objects is the summation of ixx plus iyy. So izz was not also 0, but these components were not also 0, but ixz and iyz, they were both 0. So this one was 0, and this one was 0. Now what? Am I done? So again, we get rid of omega x's and their time derivatives, omega y and the time derivatives, as well as ixz and iyz. And apparently I only have one term left. Still I have one term left. Izz omega z times this cap omega y. What is that? So in this case, we are measuring the rotation of this rigid body with respect to a stationary frame, with respect to, a secondary frame. And this secondary frame we are using to measure this omega h or anything of this object with respect to, write it on that, and then write everything with respect to the inertial frame. This guy here was only rotating about the z-axis as well. So the omega of this secondary axis, this guy, was only about the z-axis. So basically omega x was equal to omega y was equal to 0 for the secondary axis. So this guy was 0. And so now if you look, it's going to be 0 equals 0, which is of course valid, but it's not going to give you anything. So the x equation is not going to go anywhere. Okay? Because again, all of these i's and omegas and everything were 0. Now we go to the case that, what about the y equation? So let's look at the y equation. So what do we have 0 in the y equation? As I said, omega x is 0. It doesn't exist. So this whole thing can go away. Then, as I said, we don't have omega x and omega y in their time derivatives, so they're all 0. And as I said, omega x, y, xz and yz are 0. And then MOY was 0. So again, 0 equals 0. Nothing. Okay. And finally, we have this case. So what about this? Again, remember that omega x and omega y are both 0, cap omega x and cap omega y. So this whole thing is 0 and this whole thing is 0. And since ixz and yz are 0, this is 0. Now here izz and omega z, they can be non-zero, and mz can be non-zero. So that's what you get. Some moment about oz is equal to izz times d omega z over dt, which is what I said. Correct? So this only comes out of it. So again, if we want to summarize in 2D cases, we have a bunch of things equal to 0. We have all of these I components, or the other I components that are 0. These two I components are 0. The omegas are 0. And the moments are 0. And finally, these cap omegas are 0. Okay, so because all of these components are zero, the only z equation you would get in the moment is that simple one we have been using in 2D. Okay, so that's one thing I wanted to mention, and I would probably add it to the lecture. Actually, you know what, let me add it right now. Okay, so here I have added that. So these components are all zero, therefore automatically mx and my components will be zero as well. Now, so we try to always stick to the vector notation. It's way easier to deal with it this way. One more thing is the way that it's written in the textbook. This omega cross I omega term, this second term here, is written as a matrix of omega cap omega components times this I omega. And you might say, what is this? Isn't this omega a vector? Why is it now shown here as a matrix? And that's right. This is an alternative notation, and when you convert a vector into a matrix, especially this type of matrix, we call it skew symmetric matrix. This is another way that you can carry out cross product. So when we want to, in linear algebra, you can show that if you want to cross product vector A by vector B, an alternative way to do it is to form the skew symmetric matrix of vector A, make it a matrix, and then multiply it by matrix B instead of carrying out the cross product. So let me also write that for you so that you know this important thing from linear algebra. So in linear algebra, we have this theorem says if you want A times A cross B, instead of doing the cross product, another way to do it is you form a skew symmetric matrix from vector A and multiply it by vector B. Now, what is this skew symmetric operator of matrix A? So what is it? So if A is a vector like AXI plus AYJ plus AZK, then how do you form this skew symmetric? First of all, skew symmetric is the same as anti-symmetric. It means a matrix where the diagonal elements are zero, and then the components on the off diagonal, when you mirror them, for example, the component 1, 2 is the negative of 2, 1. 1, 3 is negative of 1, 3 is negative of 3, 1, and 2, 3 is negative of 3, 2. In other words, S matrix, S of A, or S of any matrix, plus the transpose of that matrix. Let me write it this way. Sum of it is equal to matrix 0. Or if you want, you can say that the matrix and the transpose of the matrix are negative of each other. So you can say it this way if you want. So if this negative was not there, the transpose of the matrix is the same as the matrix, we call it symmetric. If the transpose of the matrix is negative of the matrix, we call it anti or skew symmetric matrix. So this is the definition of a skew symmetric matrix. And you can show that in a skew symmetric matrix, the diagonal elements should all be zero. Now, this specific operator, skew symmetric A, when you define it for an arbitrary vector A, the way that the components go, the z, y, and x are positioned like this. Z, y, x, and then the z and x are negative. Z and x are negative, y is not up there. So here it is going to be AY. This is negative AZ. This is negative AX. And then when you mirror them here, you negate them. So if that was positive AY, it's negative AY. That was negative AZ, it's positive AZ. And this negative AX is positive AX. Okay, so that's how you define the skew symmetric matrix for an arbitrary vector A. And as I said, you can carry out the cross product using this operation. So let me show you very fast an example. So let's say vector A is what? 2i plus 3j minus k, and vector B is like negative I plus j and plus k. So one way is I can carry out the cross product. The other one is I form the skew symmetric matrix of vector A, which, as I said, the diagonals are all 0. AY goes here, negative AZ goes here, negative X goes here. And then you negate them when you mirror them with respect to the diagonal. So this is S of A. Then you multiply that by B, which is negative 1, 1, and 1, correct? The components. And now if you do it, it's not going to be hard, right? So it's 1, 3, it's 4. Then we have 1 and negative 2, that's negative 1. And then we have 3 and 2, 5. So the result should be 4i negative j plus 5k. And now I'll do the same thing using the determinant method that we learned in class. You can also use MATLAB if you want. But here, just to refresh your mind one more time, I'll do the determinant method. So I copy and paste the first 2 columns here and go with the Sarus's method. So here we have the 3i. So that's 3i, and then we have negative 1 times j. So that is 1j, and then we have k2, 1, so that's 2k. And then minus, we go anti-diagonal, so that's negative 3k. And parallel to that, negative I, and then parallel to that, plus 2j. So if we simplify here, I, negative I, that's 4i. You have j minus 2j, that's negative j, and then you have 2 minus 3, that's 5k. Right? So 4, negative 1, 5, which is the same as this. So this is an alternative way to carry out cross product, and that's what you have seen here. So to write it completely in matrix notation. Okay, now one other thing before we start looking at example 24 is what if, remember last time we talked about what if this secondary system we are using to sense the omega and write this omega of the object with respect to inertial, we sense it with respect to this frame. What if this frame is attached to the rigid body, right? If this frame is attached to the rigid body, it means cap omega is the same as what? Yes, small omega. And if you remember, the result of that in kinematics was if such a thing exists, then the angular acceleration is only due to change in magnitude of the omega term. So it's just going to be omega dot term, because here it's going to be omega cross omega, which is 0, right? So in case that omega was equal to omega attached to the rigid body, or the secondary frame was also stationary, which was obvious, alpha is simply omega dot. Fine. Now what about these equations? If that secondary frame, cap omega, is basically attached to the rigid body, so this cap omega is equal to small omega, Does it mean the secondary term here that you see, is that equal to 0? Is that equal to 0? Okay, is it? Is omega cross I omega is still, you know, omega cross omega is 0, but what about omega cross I omega? Because when you multiply matrix I by omega, it's not going to be parallel to the original omega vector, and so this cap omega is not parallel to that necessarily, so the cross product is not necessarily 0. So in general, the answer is no. The second term is not necessarily 0, right? You can simplify that, and you can look at different cases, right? So here, here we're gonna take a look and see in case cap omega is equal to small omega, is that going to make any changes, right? So the secondary frame is body attached. Does that make any changes? So that's what we do here. We assume that this is the same as omega z, and this is the same as omega y. So what would you get? So the first three terms are intact. They're not going to change. And I write them as dot terms so that it's more efficient notation. Now, do you have any simplifications here? So here you have positive Iyx, omega x, omega z. The other place that you might have omega x, omega z, do you see anywhere else that you have omega z, omega x? So I don't. So this is going to stay. That term is going to stay. So this is going to be plus Ixy omega x, omega z. Then you have omega z, omega y, which you can see here. This term is Izz. This term is Iyy. So no, still no simplification. So it is going to be like this. Then I have omega z squared. And here I have omega xy that I have to write. So this is going to be negative I zx omega x omega y. As I said, I have an omega y squared term. And then I have the omega z squared term. Omega z squared. So this is going to be the right hand side. Now, is there any case that anything here can go to 0 from all these 6 terms? Well, that's if the object has any symmetry about these axes, then some of these terms might be 0. For example, if the object is only has the diagonal terms, if object has only the diagonal terms, which means Ix, Y, Xz, and Yz are 0, only Xx, Yy, and Zz are non-zero, then you might get basically this term, correct? If there are symmetries, you might get, let's say, this term 0, this term 0, and this term 0. Okay, and this term. And then this one can go, and this one can go. So your equation can be quite simpler, like Ixx omega x dot plus Izz minus Iy omega y omega z. Right, so it can be quite simpler. And the same for y and the same for z, but not necessarily, okay? Not necessarily these cross inertia components are 0. Now in the example we solve, they are all 0. Not only that, even izz equals ixx and iyy is 0. So your equation is going to be way simpler. But remember that in general, the second term here is not necessarily 0. That's why the 3D rotations are a little bit more complicated. Now, not only you can write all of these equations about the fixed point O, you can also write them about the center of mass. So all of these moments can be calculated about the center of mass of the rigid body, and then all of these I terms, instead of being calculated about point O, they should all be calculated about the centroid as well. Okay, so no problem. Now let's look at this example. So here you have a vertical slender bar with mass m and length L, which is rotating on a disk that is which is attached to a disk that is rotating with angular velocity omega naught, and this omega naught is constant, and the offset between the center, the axis of the disk, and the axis of rotation is b units. So you want to know the force and the couple exerted by the disk on the bar, or by the bar on the disk, doesn't matter, right? It's third law of Newton. So you want to know if, for example, you need to keep this guy in place by a glue or bolt or whatever, what is the resultant force and what is the resultant moment that you need here to keep this guy in place while rotating. And then based on that, you can choose the appropriate glue, you can choose the appropriate bolts, rivets, whatever method of connection. So what you do here is, this is the centroid of the slender bar, which is L over 2 units above the disk and B units off center. It is rotating with angular velocity omega naught about this axis with B units offset. The XYZ axis suggested by the problem are like this. So X is radially outward, Z is basically perpendicular to X, and Y is perpendicular to the disk. So the resultant moment F and the C and the resultant force F are shown at the bottom of the bar. In addition to them, in the free body diagram, you of course have mg. And now your task is to find the F and C in this problem. So here, I'm gonna solve this problem for you. So as I said, we have 3 equations of motion for translation, 3 for rotation. So if we focus on translation, the equation is very simple. It says sum of the forces is equal to mass times acceleration. Now in this case, sum of the forces is going to be that resultant force F and then minus mg in magnitude in the negative y, so it is going to be negative mgj. This is equal to m times a. Now what is a? You know, the centroid is simply having a rotation about the fixed point with a constant omega naught. Therefore, the only acceleration it has, as you know, is the centripetal acceleration toward the center, right? So the only acceleration of this centroid is toward the center, and magnitude of it is what? As you know, it is going to be r omega squared, right? If you remember, the centripetal acceleration, it was r omega squared, correct? So in this case, r is b, omega is omega naught. So it is going to be b omega naught squared. And it is in the x direction with a negative sign. So it is going to be negative b omega naught squared in the I direction. So that is that. And so if you add them together, you can find your force F. So from here, clearly, force F is equal to negative mb omega naught squared I plus mgg. So this is the resultant force you need to keep the bar in place, to cancel out the weight and to give it the centripetal acceleration. That's all you need for force. But what about the moment? Well, for moment, we use the moment equation. We say sum of the moments, and we use the centroid, use moments about the centroid, is equal to what? The I matrix times omega components of the object, time derivative of them, plus this cap omega cross I omega. Correct? This is what we learned. Now, what is sum of the moment about the centroid? Let's go term by term and figure them out. So sum of the moments about the centroid is the couple term C, and then plus the moment of this force about the centroid. So the vector of that is what? It is this vector. This is the vector you have to use and cross product it with F to get the moment. And this vector is in magnitude clearly L over 2, and it is negative J, correct? So there's going to be negative L over 2J cross F, that resultant force. This is sum of the moments about the centroid. Now, what about this I matrix that we need? What about omega, omega dot, and so on? So as you know, omega components do not what? Change, correct? The only omega you have here for this slender bar is the same omega as the disk has, and so the only omega you have is simply what? It is omega naught, and it is about the y-axis, so it is simply omega naught j. That's your omega vector. And nothing changing here. The j does not change, omega naught does not change. So the vector omega dot is simply 0. So if I come back down here, this is 0. And this omega is known, correct? It is 0, omega naught, and 0, omega naught j. So I need to figure out this guy, and I need to figure out I. So let's first focus on I. So what is I based on this shape? So I, as we calculated the moments about the centroid, this I here should also be calculated about the centroid. So what is this I about the centroid? So if you remember, the I matrix was what? You had IXX, IYY, and IZZ. But here you had negative IXY, negative IXZ, and negative IYX, which is the same as XY, and negative IYZ, then negative IZX, and negative IZY. Correct? So what is that for this object? Clearly, since it's a slender bar, the radius of the object is almost 0. It's a very small radius. So I about the y-axis is clearly 0. And since the y-axis is the axis of symmetry of the object, IYZ and IYX also 0. So this is 0. And this is 0. What about IZX? Well, X and Z also the axis of symmetry of the object, so IZX is also 0. So the only non-zero I's you have are IXX and IZZ, and how much are they? They are the same thing, and if you remember, for a slender bar of length L and mass M, I about the centroid is ml squared over 12. So that's your I matrix. only has two non-zero elements here, and then everything else is zero. So that is your I matrix. And finally, what is cap omega? Well, in this case, the frame used with respect to which we are writing everything, this frame here, XYZ, is attached to the rigid body. So cap omega is the same as small omega. So this guy here is the same as 0 omega naught 0. And as I said, this I component, this I matrix, is ml squared over 12, 0, 0, 0, 0, 0, 0, 0, and again ml squared over 12. Okay, so if you carry out this, the first term is completely zero. The second term, you can form that matrix notation and everything. You multiply this by that, and so if you do it, let me bring this guy down a little bit. So it is going to be the skew symmetric matrix for omega times I omega. And if you remember the way that the skew symmetric matrix is defined, you put all zeros on diagonal, then non-diagonals. Here is omega y, which is omega naught in our case. Omega x and z are 0, so these two guys also 0. This is omega y, which is omega naught, and this is negative of that. So this is the skew symmetric matrix. Now if we carry out this one, so let me first carry out this. So the first element 0, second element 0, third element 0, isn't it? Yes. And so regardless of what this one is, it is going to end up being 0. So therefore, C is simply L over 2 J cross F, which is I J K L over 2J. So this vector and F, which if you remember was negative MB omega naught, and then MG and 0. So this is what we need to carry out, and you see I'm not skipping anything. I'm just doing every single term for you on the paper so that you practice all that we learned. So again, diagonal 0, next one 0, next one 0, so all 0. This one is non-zero, this one is 0, this one is 0. So the only, it's going to be negative of negative mb omega naught squared L over 2k. So if you simplify, your resultant moment is going to be mb L omega naught squared over 2 times k. So this is your resultant moment, and that F that we found up there was the resultant force. And based on those, if you know solid mechanics, you can design a good connection to keep it in place. Okay, so this is how we go about kinematics and kinetics of rigid bodies in 3D, and we try to solve more problems in class. Thank you for your attention.